The machine passed its tests. The displays looked normal. The treatment appeared to begin exactly as expected. Nothing in the room suggested that a catastrophic failure was already underway. Patients trusted the machine. Operators trusted the controls. And the people responsible for its design trusted the software. The danger wasn't visible. It wasn't loud. It wasn't an obvious mechanical failure. It was buried inside a sequence of computer instructions, and the machine no longer had all of the independent hardware safeguards that had protected earlier designs. Between 1985 and 1987, 6 known accidents involving the Therac-25 resulted in massive radiation overdoses, causing deaths and severe injuries. The machine had been designed to make radiation treatment more compact, more versatile, and more computer-controlled. Instead, its software became part of the failure itself. There is a particular kind of confidence that comes from understanding a system better than anyone else. Atomic Energy of Canada Limited had already built radiation therapy machines. The Therac-6 and Therac-20 had been used in hospitals, and their designs relied heavily on established hardware protections. The computer added convenience and control. But the underlying machines retained independent hardware safety mechanisms and interlocks. Then came the Therac-25. It was different. The machine was more compact, more versatile, and designed around computer control from the beginning. It could deliver either high-energy X-rays for deeper treatments or electron beams for more superficial treatments. That flexibility mattered. Radiation therapy depends on delivering the correct amount of energy to the correct location. Too little radiation can make treatment ineffective. Too much can cause devastating injury. The Therac-25 was supposed to give clinicians greater control over that process. And because computer control could monitor and coordinate so many functions, AECL made an important design decision. The new machine would not duplicate all of the hardware safety mechanisms used in earlier systems. Instead, more of the responsibility for maintaining safe operation would be placed on software. At the time, the decision had a logic behind it. Software could monitor conditions continuously. Software could respond quickly. Software could coordinate multiple parts of the machine. And if the software was correct, it could perform these checks without the cost and complexity of duplicating every physical safeguard. But that created a new dependency. If the software was wrong, there were fewer independent layers left to disagree with it. That distinction would become critical. The Therac-20 had independent protective circuits and mechanical interlocks. These mechanisms helped ensure that the machine's physical components were in the correct state before radiation could be delivered. The Therac-25 relied much more heavily on software to perform those safety functions. AECL had effectively decided that some of the older hardware protections did not need to be duplicated. It was not an obviously irrational decision. It was an engineering trade-off. Fewer hardware mechanisms could mean a more compact and flexible machine. But safety-critical systems have a dangerous characteristic. A component that appears redundant can become essential the moment something else fails. And there was another problem. Software from earlier Therac systems had been reused or developed from common software foundations. Some of the assumptions built into that software had existed alongside hardware safeguards. On the earlier machines, a software mistake could potentially be stopped by something physical. On the Therac-25, software had been given much more responsibility. That meant a software failure no longer necessarily had a hardware barrier waiting behind it. The system had become more dependent on the correctness of the code, and the code contained weaknesses that had not been fully exposed. The Therac-25 software controlled the machine's operating mode, energy settings, positioning, and treatment sequence. For an X-ray treatment, the machine had to move its internal components into the correct configuration before the beam could safely reach the patient. The software kept track of that process. And this is where one of the most important failures appeared. The operator interface allowed treatment information to be entered and edited. That sounds harmless. But behind the screen, multiple software tasks were operating on closely related information. The timing mattered. At Tyler, Texas, investigators found that a particular sequence of editing could create a race condition. An operator could enter a treatment setting, move away from the command line, move the cursor back, change the setting, and return to the command line, all within roughly 8 seconds. The machine's software could then treat the prescription as complete, even though the corresponding physical setup had not properly caught up with the change. The problem was not simply that someone typed too quickly. The deeper problem was that the software allowed two parts of the system to become temporarily inconsistent. One part believed the setup was ready. Another part had not completed the physical changes required for that setup. The software had lost synchronization with reality. And because the independent hardware protections were not sufficient to catch every such condition, the software could allow the treatment sequence to continue. That was the race condition. A tiny timing problem inside the code. A problem that could remain invisible during ordinary operation, until the timing was just right. Then the wrong sequence could reach the machine's treatment stage. The first known accident occurred at the Kennestone Regional Oncology Center in Georgia in June 1985. A patient undergoing radiation treatment reported feeling an intense burning sensation during the procedure. Severe radiation injury followed. But at the time, there was no obvious explanation for what had happened. The machine had not produced a clear indication that it had delivered a dangerous dose, and the incident was not immediately understood as a catastrophic machine failure. Several weeks later, another patient at a clinic in Hamilton, Ontario, suffered a massive overdose. During treatment, the machine displayed an error and indicated that no dose had been delivered. The operator attempted the treatment again. Then again. The procedure was repeated several times because the machine appeared to be reporting a malfunction rather than a dangerous radiation exposure. The patient later reported a burning sensation and severe pain. An investigation followed. But the exact cause remained uncertain. AECL suspected a hardware problem involving the machine's turntable positioning system. The machine was modified. The immediate explanation appeared to be mechanical. But the real story was becoming more complicated. More incidents followed. At first, they did not look like one connected failure. Different hospitals, different circumstances, different error messages, different symptoms, but the same machine. Between June 1985 and January 1987, investigators eventually identified 6 known Therac-25 accidents involving massive radiation overdoses. The injuries were sometimes catastrophic, and in several cases, patients died. What made the incidents especially difficult to understand was that the machine often appeared to behave normally. The operators could see a malfunction message. They could see a treatment pause. They could see displays indicating that little or no radiation had been delivered. The interface did not clearly communicate the severity of what was happening. And because operators had encountered ordinary malfunctions before, an error message did not necessarily look like a warning of catastrophic danger. The machine had effectively created a dangerous psychological loop. The system said something was wrong. Then it appeared to say that almost nothing had happened. So the operator tried again. That distinction would become one of the most important parts of the investigation. As the incidents accumulated, regulators and independent investigators began looking beyond individual mechanical failures. The U.S. Food and Drug Administration became involved. And eventually, computer scientist Nancy Levison and her colleague Clark Turner conducted a detailed investigation into the Therac-25 accidents. Their findings revealed something far more complicated than a single programming mistake. The race condition was real. But it was only one part of a much larger system failure. The investigators found problems involving software design, software reuse, testing, safety analysis, error reporting, hardware safeguards, and the way information about incidents was communicated. The Therac-25 had been given more responsibility for safety than its predecessors. But the software had not been subjected to the kind of rigorous software safety practices that such responsibility demanded. Even the original safety analysis had apparently excluded residual software errors from consideration. The assumption was essentially that extensive testing had already reduced the risk of programming errors enough that they did not need to be treated as a significant part of the safety analysis. That assumption turned out to be dangerous, because testing does not prove that a safety-critical system cannot fail. It only shows what the tests have managed to find. And the Therac-25 had a failure mode that depended on timing. That made it especially difficult to reproduce. The most famous software failure involved the operator interface. At Tyler, an operator could make a sequence of edits quickly enough that the software's internal state became inconsistent. The critical timing was roughly 8 seconds. That was approximately how long the magnet setting operation took. The operator could change the prescription while one part of the program was still working with information from the earlier setting. The software did not reliably recognize that the prescription had changed. So one part of the system could effectively say, "The treatment is ready," while the physical configuration was not actually ready for the new prescription. That is what makes race conditions so dangerous. The code does not necessarily fail every time. It fails when events occur in a particular order, within a particular timing window. Most of the time, nothing happens. Then, under the right conditions, everything happens at once. And on the Therac-25, the consequences were not a crashed computer or a frozen screen. There could be a massive radiation overdose. There was another weakness. The machine's error messages were not designed to tell operators what had actually gone wrong. The system displayed messages such as malfunction, followed by a number. But the numbers were not explained clearly in the operator manual. That mattered, because an error message is not useful simply because it exists. It has to communicate enough information for a human being to make the correct decision. If a system treats a catastrophic failure and a recoverable fault in roughly the same way, the operator can be left with the wrong mental model. And that is what happened repeatedly. Operators had become accustomed to certain machine malfunctions that did not appear to harm patients. In some incidents, they responded by clearing the error and trying again. That was understandable behavior within the system they had been given. The machine did not clearly tell them, "Stop, something catastrophic may have happened." The interface was communicating a technical problem. It was not communicating the true level of danger. At this point, it would be easy to blame the programmer, or the operator, or the hardware, but that would miss the most important lesson. The Therac-25 was a system, and systems fail through interactions. A software race condition existed. Hardware safeguards had not been duplicated to the same extent as in earlier designs. Software from earlier systems had been reused or developed from common foundations. Testing had failed to expose important timing-dependent behavior. The safety analysis had made assumptions about software reliability. Error messages failed to communicate the severity of certain failures. And information about incidents did not always move quickly or completely between users, the manufacturer, and regulators. None of these factors alone explains the entire disaster. Together, they created a system with multiple opportunities for a small software problem to become a life-threatening event. That is why calling Therac-25 simply a software bug is misleading. The bug was real, but the disaster was systemic. By 1986 and 1987, the response was becoming much more aggressive. The FDA declared the Therac-25 defective and required AECL to develop corrective measures. Those measures went far beyond fixing one line of code. They included software changes, changes to the treatment interface, changes to error handling, changes to documentation, and, critically, new independent hardware protections. UGL eventually added a hardware circuit capable of shutting down the beam independently of the software if an excessively high radiation pulse was detected. Additional hardware interlocks were also introduced. That was the crucial lesson. When software is responsible for safety, another layer should not simply trust the same software to verify itself. Independent protection matters. Redundancy matters. And sometimes the most valuable safety mechanism is the one that exists outside the system you are trying to protect. The Therac-25 disaster is often remembered as a programming failure. But the more uncomfortable lesson is about confidence. The engineers did not build a machine expecting it to kill people. They were solving a legitimate engineering problem. They wanted a machine that was smaller, more flexible, more computer-controlled, and capable of doing more with less hardware. The decision to rely more heavily on software was not inherently irrational. The problem was what happened when that confidence was combined with insufficient independent safeguards and inadequate methods for discovering how the software could fail. A safety-critical system cannot simply ask, "Does this component usually work?" It has to ask, "What happens when this component is wrong?" And then, what stops the wrong answer from becoming reality? The Therac-25 had too few independent answers to that second question. The race condition was tiny. The consequences were enormous. That is one of the most disturbing characteristics of safety-critical engineering. A failure does not have to be large to be catastrophic. It can be a timing window measured in seconds. A variable that is updated at the wrong moment. A warning that does not explain itself. A safety mechanism that was considered unnecessary. A test that never reproduces the exact sequence. Each decision can look reasonable in isolation. Together, they can create a system that fails in a way nobody expected. That is what happened with the Therac-25. The machine did not suddenly become dangerous. The danger had been distributed across the architecture long before the first patient was injured. Every safety system contains assumptions. We assume the software is correct. We assume the hardware is functioning. We assume the operator will understand the warning. We assume the test environment represents reality. We assume that if something goes wrong, another layer will catch it. But assumptions are not safeguards. A safeguard is something that still works when the assumption fails. The Therac-25 had lost some of the independent hardware protection that had existed in earlier designs. More responsibility had been transferred to software. And when the software entered a state its designers had not adequately anticipated, there was not always another independent system capable of stopping it. That is the deeper lesson. The most dangerous system is not necessarily the one with the most failures. It can be the one where every layer trusts the layer beneath it. Because when the first layer is wrong, nobody is left to disagree. The Therac-25 was supposed to use software to make radiation treatment more efficient and flexible. Instead, it demonstrated something engineers still have to remember. Efficiency can remove redundancy. And removing redundancy can remove the last thing standing between a small error and a catastrophic outcome. Which part of the Therac-25 failure stands out most to you? The race condition, the weak error messages, or the decision to rely more heavily on software for safety? Subscribe to Null Theory for more investigations into the hidden weaknesses inside the systems we trust.